Good afternoon, learners. Myself, Dr. Munish Kumar Bharadwaj from School of Engineering and Technology. The topic of today's lecture is Column Design, Part 1. As you know, this topic is related to your course Structural Design 1, ET 508A. In this course, we studied in our earlier lectures. We started with the general characteristics of the two material of the reinforced concrete, that is concrete and the reinforcement. So general characteristics of these two materials, concrete and the reinforcement, we discussed in our first lecture. Then we discussed about the design of flexural members, in which we started with singly reinforced rectangular members. Then we moved to doubly reinforced rectangular members. Then we discussed about the T-beam. Then we discussed about the consideration of shear and torsion in the design. And after doing the various aspects of the design of the beam, finally we solved a whole problem. So that way we covered in our lectures, earlier lectures, the design of the flexural members. Now we move to another structural member that we generally call as compression member. So here we will discuss today the design of the compression member or design of column. First of all, what is column? Column is a structural member which takes the axial compression force. And where it is used and what is the use of column? Columns are used to support the load of superstructure and transfer it to a column or to the foundation block. Secondly, basically a compression member, as the load acts along its axis, means this column is a compression member because load is acting along the axial axis of the column. Now this column, when we say column as a compression member, some question may come to your mind that what are the other compression members that you can see around. First of all, column you can see in various RCC buildings, in framed structures. Secondly, another compression member that you can see is the wall, means the load bearing walls in the buildings. Third, you can see the compression member in the trusses. There we call it as strut. So these are few examples of the compression members. Now column and another compression member is, we use as pedestal. So what is the difference between the column and the pedestal? When the unsupported length divided by the least lateral dimension, this ratio is more than 3, then we classify the compression member as column. If this ratio is less than 3, then we classify that compression member as pedestal. So this is some general information about the compression members and the column. Now we can see that primarily the columns are taking the axial forces along its axis, and because of that it is generally called as a compression member. But sometimes pure compressive stresses may not be there in the column. Then bending moment may occur, or the bending stresses may come in the section of the column. The reason for that bending stresses or the bending may be wind forces, earthquake forces, or some accidental loads that may be of the lateral that may be in the lateral direction. Bending may also occur due to monolithic construction and eccentricity of loads from the superstructure. So this is also the reason of the bending. Now the design of the column is primarily governed by the slenderness ratio. Means the design of a column is a function of the slenderness ratio of the column. Now when this word slenderness ratio comes into our mind, then what is this slenderness ratio? Slenderness ratio is the geometrical property of the column which can be defined as the ratio of the effective length of the column and the least lateral dimension of the column. And based on this slenderness of the column, we divide the columns into two categories. One we call as short column, another we call as long column. So this short and long columns can be classified based on the slenderness ratio, and this ratio is defined in the code as 12 if this slenderness ratio is less than or equal to 12, then we call it as a short column. If this slenderness ratio is more than 12, then we call it as long column. And this slenderness ratio of 12 value, this comes from here. You see here, this is a factor CR equal to 1.25 minus L effective, means effective length, divided by 48B, where B is the least lateral dimension. So here CR will be 1 if this ratio, effective length divided by the least lateral dimension of the column, is 12, then CR is 1. So taking this thing from this formula, so this we take to define the column or classify the column as short and the long column. But this definition or this classification is true for rectangular or circular columns. When we talk about the columns which are non-rectangular or non-circular, then this least lateral dimension we cannot find there. So there another thing comes into the picture. Instead of this least lateral dimension, we take this minimum radius of gyration. This is I minimum. And for such columns which are of the shape of non-rectangular and non-circular, this formula we use, where this CR factor is defined as 1.25 minus effective length divided by 160 and minimum radius of gyration, I minimum. If this ratio L effective divided by I minimum is 40, then CR is 1. So taking this into consideration, this value of 40, we define the columns as short when this L effective by I minimum is less than or equal to 40, or this factor CR is 1. Otherwise, we classify the column as long column. So this is the classification of columns based on the slenderness ratio. Now, in this classification, we used the word of effective length. So what is this effective length? Actually, this effective length may be defined as the factor multiplied into the clear distance or the clear length of the column. So this factor is defined or given in our code 456. One thing I would like to communicate here, that you should purchase the code IS456 to get conversant with the design of RCC. Your course material is written based on the earlier code, which is IS456 1978, but now the code available, the new code is available. This is IS456 2000. The difference, mainly difference you will find in the course material and this new code, that based on that earlier code, generally M15 concrete is also used in many problems, but in new code M15 concrete is not allowed for the construction of most of the buildings. So there we start with the M20. So what you can do, you can solve the problems that are given in your course material by replacing that M15 grade by M20, and you redo those problems, solved problems, then you will get a confidence of designing the various type of structures. So you can follow the new code and simply replace that M15 by M20 and take the characteristics of the M20 concrete while solving the problems. But it is very much important that you purchase this IS456 code. Without that you cannot design, because time to time you have to refer the code for getting the stresses of the material and various clauses that are given in the code. These are standard clauses. So I was talking about the effective length. So effective length may be defined as the distance between the point of contraflexure. As you know from your knowledge of structural analysis, the point of contraflexure are point of no movements. So the distance between the two contraflexures, point of contraflexures, is defined as the effective length. And for getting the effective length, code describes the two graphs as well as a table. In the table, ratio of this effective length are given there based on the boundary conditions of the two ends of the column. So by applying those ratios, you can get the effective length from the unsupported length. So that way you can calculate very easily the effective length of the column. Now I was discussing the types of column based on the slenderness ratio. That is the one criteria. Another criteria of classifying the columns is based on eccentricity of loads. Now when we talk about the eccentricity of load, then first question comes to our mind, that what is this eccentricity of load? If you see this picture here, this is a column section, and CG, this is black dot, is the center of gravity or the centroidal point of this section. Now if this load is coming on this section of the column, if this load acts here on the centroidal axis, then there is no eccentricity. Means when the center of gravity of the section and the point of application of the load, these two are coinciding, then in that case what happens, that there is no eccentricity. Means center of gravity of the section and the load both are coinciding. There is no eccentricity at all. Now, but in practice this is not possible because of construction problems and other problems. What happens, that this point of application of load is not always at the center of gravity of the section. This is somewhat away from the center of gravity of the section. As you can see in this figure, I have shown here that this is the center of gravity and this is load. Now this load, application of load is at a distance. If this is the CG, then load is applying here. So the distance between this CG and the load, this distance is eccentricity, which we generally represented by the English letter E. So based on this eccentricity of load, we can classify the column as axially loaded column. As I told you that when the application of load is at the CG of the section, or the eccentricity is up to a limit. Code specify that if the eccentricity is within the specified limit, then also we take it or we design the column as axially loaded column. What is that limit? That limit is if you divide the unsupported length by 500 and the least lateral dimension by 30. If you add these two, then whatever value comes are the 20 mm. So which one is greater? If E minimum is limited up to the greater value of out of these two, then we take the column as axially loaded column. Otherwise, our column will be classified as eccentrically loaded column. And where from this eccentricity comes into the picture? Why can't we design the construct a axially loaded column? The problem is that positioning of live loads. We cannot exactly define the position of live loads, because position of live loads will depend upon the nature of the occupancy and the decision of the occupants. Second thing, inaccuracies in construction, because this is very difficult to construct the column or the structure in an exact manner in which that CG of the section may coincide the applied loads or the load transferred from the other columns or the other parts of the structure. Third is the lateral loads. Generally, when there is not large wind forces or other cause of the lateral loads that we are not taking into consideration, there may be some accidental lateral loads. Because of these accidental lateral loads, this eccentricity comes into the picture. So two types of columns we define based on the eccentricity: axially loaded columns and eccentrically loaded columns. This eccentrically loaded columns, axially loaded columns first we take. Axially loaded columns we design for axial compression force, whereas the eccentrically loaded columns are designed combinedly for axial force as well as for bending moments. So this is the classification of the columns based on the eccentricity. Now we take, before going to the actual design of the columns, now we take other aspects of the design of the columns or the compression members. First is reinforcement and its detailing and the other details. Direct load and the bending moments that are coming to the column, because if we are considering the eccentrically loaded columns, then two things are there: direct loads or the compressive forces and the bending moment. So in general case, if I talk about a general case, then these two things are coming on the compression member, and these loads and the bending moments will be resisted by concrete and the steel together, because we are providing a RCC section. Here, what is the role of concrete and the reinforcement? Concrete generally takes care about the compressive forces, and reinforcement takes the role of some part of the compressive forces, and if any tensile forces are coming, that will be borne by the reinforcement. Reinforcement in the columns are of two types. One is longitudinal reinforcement. If we take this as a column, if this is column, then the bars which will be providing in the longitudinal direction, that will be the longitudinal reinforcement. That you can see here in this section of the column. This circles, small part dots in brown are the longitudinal reinforcement, and this takes care of the tension and the compression that is coming in the column section at any point. Second type of reinforcement here is transverse reinforcement, which you can see in this column section in the form of a tie shown in this red color. So this is the transverse reinforcement, which is provided in the transverse direction to the longitudinal reinforcement. So the shape which you see here in this picture is called as tie. Another type of transverse reinforcement is there, in which we provide a spiral. So that is spiral or helical reinforcement that we call. So transverse reinforcement is also provided in two shapes or two types, that is ties and the spirals. So here you see the tie. Now, what is the role of this transverse reinforcement? This transverse reinforcement is provided to prevent the longitudinal reinforcement from resisting from the buckling. Means there should not be any buckling of the longitudinal reinforcement, so it protects the longitudinal reinforcement from buckling. Second role is to resist shear force due to bending. When bending occurs, then shear forces will come into the picture. So this transverse reinforcement will take care of the shear force due to bending. Third is to confine the concrete for better ductile behavior. So these are the role of transverse reinforcement in the column. Now, code specifies certain limits to the amount of the reinforcement that should be provided to the column. First of all, we talk about the longitudinal reinforcement. The minimum reinforcement that code says should not be less than 0.8% of the gross cross-sectional area of the column, whereas the maximum limit to the longitudinal reinforcement is 6% of the gross cross-sectional area. So this is the maximum limit, 6%. But for the ease of placing and compaction of concrete, generally this maximum limit is kept within the limits of 4% of the gross cross-sectional area. Sorry. Now, code also specifies the minimum number of longitudinal bars. In rectangular section, the minimum number of bars should be 4. Means at least a bar in every corner of the rectangular section. Whereas for circular and polygon shape columns, minimum number of bars defined by the code are 6, and code also specifies the minimum diameter of these longitudinal bars. Code says that the minimum diameter of the longitudinal bars should not be less than 12 mm. Either it should be equal or more than 12 mm. And also spacing of the longitudinal bars along the periphery of the column is also specified by the code, and it says that it should not be less than 300 mm. So these are the specifications of the code regarding the longitudinal reinforcement. Now let us see some specifications about transverse reinforcement. Code says that if spacing is less than or equal to 75 mm, means if the spacing of the longitudinal bars does not exceed 75 mm on either side, then code says that transverse reinforcement should go only round the corner and alternate bars. As you can see in this picture, if the spacing of the longitudinal bars is limited to 75 mm, then means it does not exceed the 75 mm, then this transverse reinforcement should go only around the corners, these 4 corners of this section, and alternate bar. We are leaving these bars, means we are providing here, we are leaving these bars. Now we are providing around these bars. Here if you see, we are leaving these bars, we are providing around these bars. So alternatively, leaving one bar, then next bar, then leaving one bar, then next bar. So transverse reinforcement in such case should go round the corners as well, and we can provide around the alternate bars. But if the longitudinal bars are spaced at less than or equal to 48 phi, where this phi is the diameter of the transverse reinforcement, these bars. So if the spacing is that longitudinal bars spacing does not exceed 48 phi, where phi is the diameter of the transverse reinforcement, then in that case we should effectively tie the in two directions, and additional longitudinal bars in between these bars need to be tied in one direction only. Means these bars should be tied in two directions, whereas the additional bars should be tied in one direction only, as you can see here and here. So this is the specification about the transverse reinforcement, that how we should provide the transverse reinforcement. So this is the case of the transverse reinforcement. Now continuing to this transverse reinforcement, code specifies that maximum pitch of transverse reinforcement shall be the least of the following distances. First, the least lateral dimension of the column. Second, 16 times the smallest diameter of the longitudinal bars. If we are providing the longitudinal bars of different sizes, then this distance we will consider as 16 times the smallest diameter of the longitudinal bar. The third condition is 48 times the diameter of the transverse reinforcement. So out of these three, which one is the least? Then we will consider that for taking as the maximum pitch for the transverse reinforcement out of these three. Then code also says that the diameter of the reinforcement shall not be less than 1/4 of the largest diameter of the longitudinal bar and also not less than 5 mm. 1/4 of the largest diameter of the longitudinal bar, and second condition that it should also not be less than 5 mm. So this is the condition for taking the diameter of the transverse reinforcement. Now, so this was the specifications regarding the reinforcement and its detailing. Now, how to design a column or how to calculate the capacity of a column. Two types of problems generally we encounter when we design any structural member. First is the design of the structural member. Second thing is the calculation of its capacity, load taking capacity or bending moment taking capacity. So code says that this for axially loaded columns, because today we are discussing axially loaded columns. Eccentrically loaded columns we will discuss in our next lecture. So for the axially loaded columns, this either short or long, we are taking both the cases here. So this load taking capacity for the axial loaded columns will depend upon the slenderness ratio, because based on that we have classified the columns as short and the long, and the permissible load on a short column with lateral ties is given by the code as, you can see this formula, P equal to sigma cc into AC plus sigma SC into ASC. This is defined in code. You can find this in IS 456, and this is the formula for working stress method. You can find the formula for limit state method also in your code. So this is your choice, that either you can solve the problem by taking the working stress method or the limit state method. But in the new code, the more stress is on the limit state method. So better to follow the trend which is generally followed by the others. So I would suggest you to design the column by the limit state method. But here this formula you see here as working stress method, where this sigma cc is the permissible stress in direct compression, which you can find in the code. Code gives for various grades of the concrete the value of sigma cc. AC is the cross-sectional area of the concrete excluding reinforcing steel and any finishing material. Means this is the purely the cross-sectional area of the concrete excluding the reinforcement. Sigma SC is the permissible compressive stress for longitudinal reinforcement. Again you can find the value of this sigma SC in code for various grades of steel. And ASC is cross-sectional area of longitudinal reinforcement. So taking these values, you can easily find the load carrying capacity of the column. Now, the permissible load for a short column with helical reinforcement. Earlier one that we discussed was for a ties, when the transverse reinforcement is provided in the form of ties. But if we provide the transverse reinforcement in the form of spiral or helical reinforcement, then a slight difference comes into the picture. And what is that difference? That the load carrying capacity or the permissible load becomes 1.05 times the permissible load calculated by the earlier equation, means for the tied columns. Here means what we do, we increase the permissible load by 5%, which we calculated for the case of the tied short column. In case of spiral or the helical reinforcement, you will increase the permissible load by 5%. Means you will multiply the load calculated for a tied short column, you multiply it by 1.05, then the load permissible for the spirally or the spiral short column you can find that way. But here there is a condition, that this condition should be fulfilled if you increase that value by 5%. And what is that condition? That volume of the helical reinforcement divided by the volume of the core of the column, here you see this formula, should be less than 0.36 times AG, means the gross cross-sectional area of the column, divided by AC, means the cross-sectional area for concrete, minus 1 into FCK upon Fy. FCK is characteristic strength of the concrete and Fy is the strength of the steel. These notations you know very well. So AG, gross cross-sectional area, AC, area of core of the helical reinforcement column measured to the outside diameter of the helix, and Fy is the characteristic strength of helical reinforcement, but not exceeding 415 Newton per mm square. Means you cannot take the steel grade more than Fe 415 for providing the transverse reinforcement. That is the meaning here. So this Fy is for helical reinforcement or the transverse reinforcement here in this formula. So if this condition is fulfilled, then you can increase the permissible load by 5% for the spiral short column. Now let's take one example of the column design. Here the example problem says that a column of unsupported length of 4.5 meter and cross-sectional area 250 by 250, means square column, is reinforced with 4 number of bars of 16 mm diameter. Okay, so this is longitudinal reinforcement. Determine the permissible load if both ends are effectively held in position but not restrained against rotation. Means this last line gives you the boundary condition at the two ends of the column. So keeping in view the boundary condition at the two ends of the column, you will calculate the effective length of the column. And this problem says that use M15 concrete and Fe 415 steel. Okay. Now what we will do permissible load for a short column, assuming that it is a short column. First we will start with this load. Permissible load can be calculated as sigma Cc into AC plus sigma Sc into ASC. That you know, that I told you that formula. Now for calculating of that area of concrete, here what we can do, in place of AC we can put the value as AG minus ASC. Means this is a gross cross-sectional area of the column and this is the area of the steel. So if you subtract this area of the steel from the gross cross-sectional area of the column, then you can get the value of the area of the concrete of the cross-section. So sigma Cc into Ag minus Asc plus sigma Sc into Asc. Now put the values. Here Ag you can calculate 250 into 250 simply because it is a square column. Sigma Cc for M15, this 4 MPa is given in the code, so 4 we have taken as sigma Cc here, minus the area of the steel. As you know, 4 bars are given, so 4 into area of 1 bar, and area of 1 bar you can calculate pi by 4 into d square. So here you can calculate this part, first part of this formula. Now for the second part, sigma Sc into Asc, you can write sigma Sc, this is the permissible stress in steel in compression, which you can get from the code, 130 MPa into the area of the longitudinal reinforcement. So this is 4 bars into area of 1 bar, pi by 4 into 16 square. So that way we get the value of 351.34 kilonewton. This is the permissible load. Now let's check the type of column. So calculate the slenderness ratio of the column. Unsupported length in the problem is given as 4.5 meter. Okay, and for the given boundary conditions, what says that both ends are effectively held in position but not restrained against rotation. So for this case in the code you will find that the coefficient or the ratio for that effective length is 1 there. So multiply this unsupported length into 1, then this 4.5 into 1 means 4.5 meter. So effective length is equal to the unsupported length for this given case. And the slenderness ratio you can calculate as effective length divided by least lateral dimension. Least lateral dimension here, both sides are 250, so B will be 250. So here we calculated slenderness ratio as 18, which is more than 12. So if you know that if the slenderness ratio is more than 12, means the column is slender. So what we will do, we will apply the reduction coefficient to the permissible load, because for slender columns we apply this reduction coefficient on the permissible load, and the formula given in the code is this 1.25 minus L effective divided by 48B. So 1.25 minus L effective 4.5 meter means in mm this becomes 4500, and 48 into B. B is the least lateral dimension, which is 250 mm. So from here we get this reduction coefficient as 0.875. So we will apply this 0.875 reduction coefficient on the permissible load that we calculated for the short column. Then multiply it by this earlier value, we get the value of 307.42. So from here we learned that we can calculate the permissible load for a slender column just by first we calculate the permissible load for the short column, and we calculate the slenderness of the column. If the column comes out to be slender, then we can apply the reduction coefficient to the permissible load that we calculated for the short column. So that way we can find the value for the slender column or the long column. So this is the way how we can calculate the load carrying capacity of the column. So in this lecture I discussed about that what is compression member, what is column, how the column is different from pedestal. Then I told you the types of column based on the two things. One is the slenderness ratio of the column, second was the eccentricity of the load. Then I told you about the reinforcement and the other details of the columns. Then I gave you one example of how we can calculate the load carrying capacity of the column. So that way this lecture here I stop, and I expect you to go through your course material. In that course material some more examples are given there, so you go through the examples given there, practice them, and I again suggest you to use the new code and replace this M15 grade concrete by M20 and redo the solved problems. So we will meet in the next lecture. So thank you for patient listening.